Oops. So, hello everybody, and welcome to my fourth session on statistical energy analysis and hybrid methods. This time we will talk about random processes and the treatment of random signals and systems. And as the name random is saying, it will be the first big step towards statistical energy analysis, because there are a lot of random signals in our systems. Okay, so let's go. Why do we need that? I mean, in technical processes, we rarely have classical harmonic signals. So we have many signals that are more random-like. It could be, for instance, a turbulent boundary layer flow or turbulent flow in general. Rain on the roof. It's raining today, so a good example. Or for example, the combustion in a jet. That's a random process, more or less. And so we need formulations how to describe these processes and how to understand the spectral content of them. And the good thing for this is classically the Fourier analysis, which is the theoretical link between a periodic and harmonic, but also a transient time signal. This theory will not be trained so much in detail, but that's not too critical. Please keep in mind that this is a free chapter of my book, available here as given in the link. So here you will find a short wrap-up of everything that is required to understand the convention and the basic theory about Fourier analysis. Okay, so far for that. Let's come back to the lecture. And again, as mentioned, classical harmonic signals are rare. So we need something to treat non-harmonic signals. And but also, and this is also very important, is the Fourier theory. It could also be applied to stochastic and random signals, but this has to be done in a different manner. Not the same as for the typical harmonic signals, periodic signals that we use in Fourier theory sometimes. Okay, it's definitely an important toolset for the description of vibroacoustic system, because I mean this is a typical way of excitation response of such a system, and this means that we need a toolset to describe and to manage those things. And very important, and this is, I think, for most of you, a typical obvious thing, as you are from the younger generation, all spectra and signals, they are today available as discrete digital series. So the time of analytical test devices has come to at least nearly an end. Okay, let's start with some definitions. So first of all, just imagine that we have a random process like this. So it's several time experiments and leading to different results, which are given by the quantity f. And we start to define the probability, which is the probability that a signal or a result or whatever is below a certain value. So that means that this is the probability that this f is below a value fk. And this is given by the function p, capital P, from f. At the same time, this is a train, also a random signal, hopefully not too noisy here, so it has passed. We can at the same time define the probability that the result of this process or signal is in a specific band, say from delta f from f2 to from f1 to f2, and this is what we call the probability density function. And we define this by taking the limit according to make this delta, and the limit goes to 0, and this is the probability density. So the dependency, I mean, this is a different way of creating a derivative, and the relationship between both is that the probability density is the derivative of probability with respect to f. If we present both signals in a diagram as it can be seen here, so that is the red curve is the probability that a signal is below a specific value. It's approaching 1 for infinite values, obviously. and the probability density is the derivative of it, and you see you can identify a specific maximum. So this is the area where the probability density for a specific result is the highest. Obviously, this here in our example is the case around 0. No? Good. We can also go the other way, so we can create the probability for a specific interval or whatever, and this can be easily derived by using the integral from two specific values of f using the probability density, or because that's the integral using the typical math, it could be it's a difference between the probability function of both test results. Good. So we talk about we talk a lot about time histories or experiments or signals, and this is the time to clarify some specific things, because when we do averaging here in the principle we average over an ensemble of tests or an ensemble of experiments, and this is denoted by this brackets, this kind of brackets with an E. And it means that you repeat the experiments several times, doing always the same and taking, for instance, a specific value at a specific time, t1, for instance. This is not the same as taking a very long history and cutting out specific windows of it. It could be the same, as we will learn later, but it doesn't have to be naturally the same. There's a specific kind of processes and signal that allows for that, but this has to be specified in more detail later. Okay, so starting from all the probability densities and so on, now we have to quantify some other quantities, and this is the mean and the mean square value, and this is what we'll talk about next. So just imagine that we have an experiment that is repeated 100 times. As shown here, you get a specific result, which is fi, if it's a discrete value, and you average over all those results. And this is the so-called mean value that we can get. And again here, this is a process, this is symmetric about 0, so the mean value of this would be 0, roundabout. We can just imagine that we have a discrete experiment. It could be a coin where you have just two discrete results. It would be 1 and 2, or you can you take a dice and you have something between 1 and 6, and we just count all the occurrence of, let's say, the 1 of the dice of over 100 experiments, and this is what we call then the frequency of the result, denoted by R index k. Then we can rewrite this a little bit in a different manner. So that means we have now the interval. So for dices it would be a 6. For coin the nk would be 2. We sum all this up and we take the single frequency of the occurrence of the specific value at the dice. So if you make infinite dice experiments, it would be 1/6 for the frequency. It would be the value 1 to 6 for the fk, and here we would have the value of 6. So that would be the average of all dicing experiments. Again, we can reformulate things a little bit when we define this using our probability density function again. Multiply this by our delta. So let's say our interval that we have for the result of this probability, and then we can reformulate this in a kind of continuous form. So we have the probability density, the result of the experiment times this delta function. So this would be, for instance, if we take the example here from above, that would be the line would be our probability density function, and this would be the outcome of our experiment. Again, it's an experiment, so it does not fit perfectly to the probability density. But if we go to 1 million, 2 billion, whatever higher numbers, it would be smoother and smoother. But for counting this, we need specific intervals, which is denoted here by the orange bars. We can perform the limit, we go to a continuous value and reformulate this sum again in terms of an interval. And if you do so, we will get a description of our expected value of our mean value based on the function result and the probability density function. And this is very important. So that means once we know the probability density, we can directly identify all the expected values of one specific process, whatever we are interested in. Good. So this was the mean value, and now we talk about the mean square value. Same story, more or less. The only difference is that we are not using fk, we are using fk square. And we denote this by using the value for expected value or the brackets, and we can also use the continuous form using the square here in this formulation again. We use an example here too. So this is just the square of the test experiment, so everything is, that's logical, nothing is below 0. And this time we got, for this mean square value, we got a result which is the mean square value, and that is here the orange line. And this is very helpful quantity, especially if we have mean values which are somewhere in 0. And there is an expression which we call the variance, which is the kind, let's say, the normalized way of this. So that means if we take the single test result and we subtract the mean value from this, we get the variance. It means it's a variation of our test result from the mean value. Here in the experiment, the mean value was 0. So in this case, if the expected value is 0, that means that the mean square value and the variance is similar. Good. So now it's time to formulate a little bit what kind of processes allows to treat ensemble averaging and time averaging in a similar way. And this is what we call ergodic processes. So the process is called ergodic when the ensemble averaging can be replaced by time averaging. So now we don't count hundreds of experiments, we just do the same experiment over time, and that means that we just averaging over a time history. So going from t half minus to t half, and the averaging is done by doing the integration and then divide by the time interval. And we can use the same definitions or similar definitions as before. So that means this is our mean value and this is our mean square value of the given time history. Good. So we have introduced some probability density, probability functions. We have defined a mean value. We have defined a mean square value. Now it's time to start with something that is much more important. And this is the correlation. Because the correlation, it defines how one random process is linearly linked to the other one. Or let's say, coming back to our vibroacoustic topic, if you make a microphone test at one position and you make another microphone test at another position, you must understand what is the statistical relationship between both of them. The terminology that's used here, that's correlation. That's a very important thing, and it is a very important thing in statistical energy analysis. So this is why we are doing this here. So just imagine that we have two random processes, f and g von t. To keep things simple, we say they both have 0 mean values, which is absolutely okay. Then let us consider that we suppose that g is linked to f by some linear factor capital K. So it's a hypothesis. And as this is just a hypothesis, the question is we need to define a deviation of this assumption, and this is called we use a symbol delta for this. So that's the difference between the real result of the time history g minus this so-called linear relationship to f. So if we square this and we would like to have the mean square value of this, and we call this j, we would have to find the expected value of this expression here. Give me some time, so that means this is where we have to calculate the expected value from. And if we rewrite this a little bit and rearrange things, then we would get we just summing or we squaring this out, and we'd have an expected value of g of f squared times some factors, and very important, of combination. So g multiplied by f. Good. That's a minimization problem, and we have to look for the slope k that minimizes this sum of squared deviations j. That's the mathematical job that we have to do there. Before we go into the math, just to give you an idea what that could mean. So it's here on the right hand side, on the upper right hand side, you see an example for two processes that are not correlated at all. You will later see what the quantity here means. So, but every dot that you have here has no linear relationship to the result in G. So it could be everywhere, and that it's just a cloud of dots. If you would have some specific relationship, take the blue cloud line here, you see every result of f leads to something that is in the area of this linear function, and you can, this cloud is along a line, and this is which is a hint that there must be some kind of correlation. Obviously, for the blue line, this is much higher than for the orange line, which you can also see here with those values that we will derive in the next steps. Good. As mentioned, it's a quadratic dependence, and we have to find this the minimum of this, which is should not be too complicated. We use some acronyms A, B, and C with those quantities here that I will not go too much into detail, but we just have to place them later. So this equation is parabolic, and the minimum can be found by finding the zero of the derivative, and that's not too heavy calculation. That can be quite easily done, and then we find that k0, so the optimum slope, is minus b divided by a. So on top of that, to prove that this is really the minimum, it is required that the double derivative or the square derivative is larger than 0, which is obviously the case because it is something like a that we need an a that is large, or which is the expected value of f square, and this is naturally always larger than 0, so it's definitely a minimum. And if we substitute k0 into equation 33 again, we get all the relationship that we need to calculate k, so the optimal slope, which is leading to the k that you see here in the diagrams. And where you see also a quantity determining the error, so the deviation, which is J0, so the best or the minimum error or deviation that we can find. When we rewrite this term here in a slightly different manner by normalizing it by the variance of G, it would look like this. It will be 1 minus the expected value of the combination or the product of f and g divided by the variances of f and of g, and then we would get this expression here. And this expression, the last one here, which is the quantity denoted by Greek symbol rho fg, this is what we call the normalized correlation coefficient between f and g. And this now explains what the figures here is meaning. So 0 means that you nearly have no correlation at all. So both processes are completely uncorrelated. If they are approaching 1, the processes are quite well correlated. And perfect line would be a perfect 1 for this correlation coefficient. Good. So now we have done this for single events or single time steps or whatever. And now let's see what happens if we use something like this for two processes and we measure them at different times. So at t1 and at time 2. And we would write this down in such a way. So we just have to, in the function, we just have to note the single time points from the history. We call this numerator the cross-correlation function. So it's the expected value of two functions multiplied by each other, but using different time steps. When we talk about a stationary process, that means that we don't have to consider the exact time position. We just can rely on the distance between the two histories. So we replace the second time by t plus tau, or we just use t and not t1, and then you would get this as the cross correlation function. Then tau is the distance between the two time points. Good. It also makes sense to correlate the function itself, also to correlate a function at one time to a later moment ft plus tau. And this is called the autocorrelation function. We would write it like this. It's very important to note what is the value of this function at specific values, and tau equals 0 is quite important because this is exactly the variance, because this is just the squared f function, and this is, as we know, the variance of f of t. Good. So, some properties. The autocorrelation is symmetric in time. That can be easily proven. So we just have to replace t via t minus tau, and then we can find the relationship that it is equal to minus tau. We can also use some very important properties regarding the cross correlation function. So we can do the same, replace it, and then we see that if we exchange g and f, it would be the same with a negative tau argument. So written here in short like this: exchanging f and g means negative time distance argument in the cross correlation function. For static ergodic processes, we can again replace the ensemble averaging by the average over time. This would be something like this. And now it's time to give you, let's say, a demonstration for this formulation, and what it means. What is the physical, natural meaning of the cross correlation? So here, just consider two functions which are somehow steps. That's the triangular step functions, the blue one, and the rectangular step function, which is the orange one. And we have shown some time steps for different taus. So that means that the orange, so the blue function remains unchanged, and the orange is moving from time to time from the right to the left. And if we multiply this, we see that if the overlapping area is always denoted by this black. So when it enters the field, you get some, you get a step-like result of this function. So physically, the correlation of two functions can really be understood as some kind of pattern comparison. So the function in shape, the shapes of those two functions must fit together. Otherwise, there would be no correlation. So this is a good tool if you have some similar signals. You can similar structures on the time history, on the time signal, and that this is a measure to identify, for instance, or if a signal is coming from the same source, and that's very helpful in vibroacoustic testing, because all non-correlated signals, so a signal from the wrong source, maybe a disturbing thing somewhere in your test equipment, that's filtered out. That's an important feature. Now we just had a look at the filtering out the train again. Hopefully good. So the train is over. If we just do the final cross correlation of it, you see that is the blue line. So this is then the integral over this black shape, and then we would get this kind of function. That means we get some peak-like shape. And this peak means that at the moment of tau equals 0, the functions or the time histories are signals, and the patterns fit quite well together. That is the outcome of this cross-correlation function. Good. As mentioned, I will not go too much into detail of Fourier analysis. As you have seen, there's a free chapter where you will find all the details. That's linked in the PDF, but I will put it in the comments and the description on my website. I will not go to here in detail. These are many useful formulations and relationships of Fourier theory, especially for delta function, what happens with single power, what is the derivative, and so on. Just one important thing is really important to note. If we use this convention for the Fourier transform, using the minus j omega t term in the exponential function, this corresponds exactly to the plus j omega t convention in the time history, as mentioned very before, because in this case the time derivative is j omega f. If we would have used another convention, it would be minus again. So it's very important, especially if you're using other literature, other textbooks, please check that the time convention of your complex singles fits to your Fourier transform. This is guaranteed here if I use this convention. And also important is, you know, that between the transformation and back transformation, you are free in distributing your 1 to the fraction of 2 pi factor. You can use a square root or whatever, put it there. In this book or lecture, I use always the back transformation is using the 2 pi here. Good. Okay, so far for this. Please refer to the free chapter, then you see the details there. And we will continue now our Fourier analysis of random signals. Just imagine that we have a random signal. It goes like a white noise going all over the day. You can't use classical Fourier theory because it's an infinite signal with infinite energy, and that's not possible to use a Fourier analysis with that. But what is an easy option to overcome this issue is just take the Fourier transform of the autocorrelation, not of the signal itself. This is what we have here. So this is our autocorrelation function, and we take the Fourier transform and the Fourier back transform of this. This is what we call the autospectral density of a time signal, and it's a measure how the signal energy is distributed over the frequency range. So you get a spectral energy content. Very important. And again, some specific values are important. For tau equals 0, this is again the mean square value of this function. So the 0 value of our cross of the autocorrelation is always related to the mean square value. Good. Some properties and other important properties. The autocorrelation is real and symmetric function. So that means that the autospectrum is a symmetric real valued function of frequency. So this is hopefully denoted by using this is why I'm using not non-complex symbol convention. So this is not italic bold. The cross-spectral density is the Fourier transform of the cross correlation, which is defined by this. So similar than here. The only difference is that we have exchanged the function that is transformed. Also here some important properties. If we exchange f and g, we have to use a negative x-axis. So if we exchange the relationship between the two signals, we have to shift or rotate the frequency axis. This was a study using more or less theoretical considerations with long averaging and long intervals. If we do tests, we never have an infinite test time available. We have a specific test time and we have specific time slots. Now it's very important to find a link how to generate such results from signals of finite time. So we define Fourier transform of 2 random signals, but now we are just using a specific time interval, not the from minus infinity to plus infinity, and this is what we called fk and gk. So there's a very lengthy and good proof in the book from Bendert and Pearsall, given here as reference 4. You should find in the reference list. And this gives, it's a very important and practical thing. So if we do an expected value of many time, let's say, intervals, if we use infinite time again, I mean, it's a theoretical consideration, but just as a first proof, we see that we could calculate the cross correlation, the cross spectral density from the expected value of the complex Fourier transform of K multiplied by the complex Fourier transform of G. So we don't have to do all this correlation function derivation and then Fourier transform it. It is much better to make the Fourier transform of each of our singles and do an averaging over several Fourier transforms. And that's a big step and makes the signal analysis much easier. And by the way, this is how it's actually done in all testing measurement systems. You don't do a classical correlation procedure because that's very costly. So if we have taken, if we have a finite, here we take the signal. Again, mentioned we have infinite iteration, but however, and we can do the same for the autospectrum. Just another definition. We can use, we can just average over many spectra that we have taken. It could be ensemble average, but as it's ergodic, we can snap out different intervals in our long-lasting signal. So again, what holds for the cross-spectral density obviously also holds for the autospectrum. Good. So again, and just introducing a new acronym. If we calculate the cross-spectral density, we just take the expected value of f times g. And the first function has to be conjugate complex. Good. So last time, again, here, this is all derived and explained for the case when we have, again, an infinite time interval available, which we, as mentioned, don't have. So here we took an ensemble of signals of infinite iteration, which we obviously not have very often. So what happens if we take a finite iteration of time interval t, and we separate this into m partitions of length t w for window, and then we would call this here by this hat symbol, and we would get, let's say, but this averaging would be, we would get this averaging result here. And it's also shown that the relative error that we get, so that means this is our original cross correlation, cross spectral density, and this is the estimated cross spectral density derived by this average over a specific but finite set of time windows m. And then we learn that the error is getting lower and lower the more averaging we do. But keep in mind, if we have one fixed time t and we can divide it into 2, 4, 3 or 1000 intervals, we will lose spectral resolution, because the longer our time interval is, the higher is the spectral resolution. So at the end of the day, if you would like to have a very precise estimation of our cross-spectral density, we have to sacrifice spectral resolution. This is the compromise that we will have to find. And by the way, that's the signal analysis feature of representation of the Heisenberg uncertainty relationship from quantum physics. Good. Okay. So that's it from my side for random processes. Thank you very much for your heavy attention. I mean, this time it was quite heavy stuff. Lots of definitions, maybe quite boring, but believe me, it's extremely important for the next session, because now we will talk about systems. We will talk about systems of multiple input and output, and very important, how such systems answer, or what is the response of such systems when they are excited by random and partly random signals. For this excitation and response calculation, we need all these famous cross-correlation functions and whatever that I've shown you before. If you have questions, comments, contact me on the author page. And again, next week we will talk about these systems as mentioned here. So have a nice day. Bye bye.